Okay, welcome everybody. So today we have the pleasure of welcoming Maurizio Grasselli from Politecnico di Milano. We'll talk about non-local incompressible candidial fluids.
Thank you very much. So thank you very much for being here, and let me thank the organizers of the seminar for this very kind invitation to this hotspot of mathematics in the world. And this is a particular occasion today. You see here, I underline the fact that it's the World Day of Mathematics. It's here, you see. I mean, we have to use the notation, the US notation. 3.14 is almost pi, so it's the pi day. So it's a particular occasion to give a talk on mathematics. Okay. I'm going to talk about this subject, but before introducing equations, let's talk about recipes. I mean, for instance, it's a bit that can we?
Yeah, sure. You
Just
okay.
Because the title is important. Okay. Okay. Yes. Let's start with the recipe, which should be well known here. And you take some olive oil, some vinegar, some mustard, salt and pepper, and then you know the recipe. I don't read it. And then the result is this. So quite a homogeneous mixture. But if you miss one ingredient, in particular, if you miss mustard, then the result is a bit different because you have and why? I mean, you have this, and I can refer to a recent paper in physics of fluids, so it's a serious thing, not just a joke. Cooking. Okay. Yes. Cooking is especially here and in Italy, of course. I mean, it's a serious thing. So, and why this happens? I don't want to anticipate why this happens because this is the subject of my talk, but keep it in mind. So you have these droplets in a sea of oil. Okay. Of course, if you try to stir, then maybe you have some mixing. But if you wait for some time, and of course the temperature plays a role in the sense that if you have a very high temperature, everything is mixed. Entropy prevails, but if the temperature is low enough, I mean, room temperature, for instance, then the result is this. Okay, but there is another news. I mean, that was a French recipe. Now let's talk about an Italian recipe. Okay. An Italian recipe is cacio e pepe. I don't know. I mean, the Italians here know, of course, but maybe the French don't know this recipe, which is very good. It's a kind of pasta with this sauce, which is called cacio e pepe. Cacio is a kind of cheese, and pepe is pepper. And here you have a simple ingredients. I mean, you have pasta, pecorino cheese, and pepper. But you have to be very careful because if the starch concentration is below, okay, below the cheese mass, essentially, then you start seeing some clumps, okay, and this is not good because you need a homogeneous mixture as before, okay. So even here, I mean, you have a phenomenon which is very similar to the one I just showed to you regarding the vinegar. Okay, and also this has been published in Face Behavior of Cacio e Pepe sauce. Okay, but you may wonder, okay, but these guys are, I mean, these guys are strong nuts. Bartolucci and also the other co-authors are very strong nuts. So they are not writing papers, I mean, just to have some fun. It's a serious matter. Okay, so that's enough for the kitchen. Let me just show you this. The optimal result is this. You see a creamy sauce without lumps, okay? But you have to be very careful, okay? Like for vinegar. Okay. So what is the phenomenon hidden behind? The phenomenon is phase separation. And phase separation is a competition between two phenomena, entropy from one side and the mixing on the other side. Okay. So, for instance, in the case of vinaigrette, vinegar molecules tend to stay together to minimize the energy. But of course, they have to compete with entropy. So it's a competition. That's the reason why you observe this pattern, which is quite, can be quite complicated. Okay? It's not homogeneous. Of course, let me stress that this depends on the temperature. Okay? And so this is a cartoon which shows, what's going on, what I just told you. Okay? The mixing reduces the energy, the free energy. Okay, but it's a competition. So you expect to have something, a free energy, say, an energy, which is not just convex, but it has a double value. Okay, because you have two phases, but you can also stay in the middle. Okay. Okay. Before introducing the equations, I would like to stress again that phase separation is very important. You don't need to read it this, but let me just stress that this appears in Nature, and this is not a scientific paper, but it's an introductory, a review paper, because phase separation is so important, especially in biology. It has become so important that if you browse any kind of issue of Nature in the last years, and there is at least a paper in phase separation. Why? Phase separation was already known, of course, in material science, for instance, in many other areas, actually. But now, recently, in the last years, it has become a very important phenomenon in cell biology. And the two guys and their collaborators who discovered that, essentially, discovered this mechanism, one is Bin in Princeton, and another one is a German guy. They both won the Breakthrough Prize last year for life science. And the point is that phase separation is a mechanism which takes place in the cell, and it aggregates essentially the droplets of proteins and RNA aggregates to form this it's called condensates. It's like the droplets of vinegar. Okay, but this kind of process and the way they form, these condensates form, plays a very important role in the health of the cell, we can say. If this process has some defects, then it can lead to disease, very important disease. So it's still a world which is under exploration, but there are more and more evidences which show that this phase separation process going on at the cellular level can play a very important role in many of the cell functions. Okay. And here it's explained in why, in a more explicit way. So it's a key organizing principle of the cell. And so clusters of proteins, as I told you, nucleic acids they form specialized units which are called condensates. And the point is that they are very important in many functions of the cell. Okay, I don't want to enter into the details because I discovered that biology is a very, very complicated subject. I would say much more complicated than mathematics. Okay, they have so many names and so many theories, sometimes conflicting ones. So, and also this paper has been, this review, this divulgatory papers has appeared recently. So I can, if you are interested in looking more closely at what's going on from the biological point of view, you can. So I hope that with this introduction, I convinced you that phase separations is worth studying. Okay. So now let's talk about how to model this kind of phenomenon. Because if you wanted to write down decent equations, you have to understand what kind of equation you can do. So a way is the following. if we denote by phi the relative concentration difference, for instance, between oil and vinegar, and you define the mixing, for instance, the Boltzmann-Gibbs entropy density, there are other definitions of entropy density. This is not the only one, but this is the most usual one. And you assume that the mixing energy density as this form. This is very simple. You can also use more complicated form, but this is very simple. And you can understand that this is minimized where? When you have pure phases. Okay. So 1 or -1. Okay. And then you formulate, you introduce this free energy density where theta is the absolute temperature. Then you realize that there is a competition between between entropy and between the mix. Okay. And it's not convex if chi, this one, is greater than theta. Okay, is a double well shape. Okay, more precisely, there's a shape of this type. Okay. Okay, you look at the blue line. Okay, I also draw here. I also chose this picture with the red line because sometimes in the literature, actually very often, the logarithmic potential, I mean the logarithm, the Boltzmann-Gibbs entropy, is approximated by a polynomial function. But this is not completely satisfactory because if you do that, I will come back to this. If you do that, then mathematically you lose a very important property. I mean, you lose the property of, but you can understand that only when I wrote down when I will write down the equations. You lose the property of having phi in between -1 and 1. Okay, because you no longer have a maximum principle. So it's an approximation which works numerically, but it's not a complete satisfaction. That's the reason why I chose this picture. Okay, so which equations? So you integrate your free energy density, okay, and the most natural thing to do is to calculate the functional derivative of W, and then to write down a conserved gradient flow, okay, for this kind of process. And if you don't have sources, you can imagine that the evolution process is driven by a gradient flow. Okay. But if you do this, you see, since F prime since F is a double well, okay, that equation, okay, if you write down that equation gives a nil-post problem. Okay, so it doesn't work. Okay, so this is the most naive approach, but it doesn't work. And for this reason, back in the 1950s, Canedilia proposed a free energy of this form, in which you have a penalization term of this kind, which allows the formation of diffuse interfaces separating the pure phases. Okay, and these diffuse interfaces are of thickness epsilon. Okay, and so you can imagine that in this case, I mean, you pay a price in the sense that you have a very concentrated subregions in which you have mixed phases. Okay, but it's good. I mean, it works. Also physically, it's expected. And moreover, I just remind you this: for whoever knows, for instance, the Monica-Mortola function, you know that when you take the epsilon and you use gamma convergence and you take it epsilon goes to 0, then you go back to a problem which is exactly what you expect. I mean, the sharp interfaces separating the two phases. Okay? And this kind of choice, if you use this energy and you define mu, which is called the chemical potential, as the functional derivative of the energy, and you formulate a gradient flow taking also a mobility, because the mobility, for instance, can be positive, but can be 0 at the pure phases because nothing moves there, for instance. Then you end up with the classical Canadian equation, okay, which has been studied by many. So that's an That's a well-posed problem. I mean, well-posed in principle, because for that equation, if you take a mobility which is degenerate, the only theoretical result which is known is the existence of a well-unique solution. So well-posed. If the mobility is constant, many things. Okay. But that's not the only version of the Canadian equation. There is another version which is closer somehow to a microscopic point of view. Okay, in the sense that the former Canadian equation is a phenomenological equation. Okay, it's not justified like physicists do. You take a microscopic model and then you take some probabilistic limit and you end up with a macroscopic equation. Okay? But if you change your a little bit your point of view and you change the energy, then you can end up with another version of the Canadian equation, which is a non-local one, which is satisfactory, much more satisfactory than the former one concerning theoretical results. And moreover, it can be justified. It has been justified in the way I just mentioned. I mean, from microscopic to macroscopic. And there are two different approaches. And in a periodic domain, they are equivalent. Namely, you always keep your entropy. And instead of assuming that the mixing term is minus some positive constant times phi squared, you assume that it's non-local through a kernel, which can be, for instance, a Newtonian kernel. Okay, that's a typical case. Okay. And this is very frequent in physics. Okay. This is a typical Hamiltonian. If you do that, okay, and you formulate the same equation, okay, but where the chemical potential is this format, where this is the convolution over omega, in that case, the equation is well posed, but in that case, it's really well posed, even when the mobility is degenerate. So you have a complete picture for the theoretical point of view. Recent results, I'm not talking, these results are very recent, in the last 10 years. Okay, there is an alternative point of view concerning the non-local approach, in the sense that instead of taking a non-local model of the mixing, you take a non-local version of the gradient, okay, in this way. Okay. That's also typical. It's not the fractional Laplacian because J is smooth. J is not single. Okay. But it works. Of course, when you calculate the chemical potential, you just have this term. The only difference is here, okay, where this is a coefficient depending on x times phi. So it's a difference of order 0, linear. Okay. In a periodic domain, this is constant. It's not completely easy to prove that it's constant. So that if you take this equal to chi, be careful because this is a double well, it's no longer the entropy, okay? Then the two non-local Canadian equations, I mean, the one before and this one are completely equivalent. The same. Okay. And in that case, in the periodic domain case, then Giacomini and Lebowitz, at the end of the 90s, proved that this is a macroscopic model obtained through a hydrodynamic limit for a microscopic model of aggregation. Okay. So it's well justified, for instance, for a physicist. Okay. Okay, so the differences are very tiny in the sense that in terms of well-posedness, the presence of this term or not doesn't make any difference. The only difference is when you want to connect the original Canadian model with the non-local one. In that case, you have to keep this, because if you take this of an appropriate shape, depending on a parameter, and you perform the right limit, it's not easy, but you can do it. Then you recover the original Cannier equation where here you have just the gradient square. Okay. There is a series of recent results about this. In the other case, you cannot do that because you are not approximating the gradient square. You are approximating the remixing. You are making the remixing non-local. So it's a different point of view. In the periodic domain, it's the same. Okay. So, but now we have to take we have to take care of the liquid structure because we are talking about fluids. Okay? We are talking about two-phase fluids like olive oil and vinegar flavor. And so in this case, the diffuse interface which separates the two phases is transported by the flow. And so the Cannier equation must have an advective term. Okay? And moreover, if we consider the Navier-Stokes equation formulated for a volume average velocity, so here you don't have a sharp interface in which you have two Navier-Stokes systems, you have a surface which separates the two fluids with conditions on the free band. Okay, that's another point of view. It's a diffuse interface model. So you have the Cannier equation all over the domain, and also the Navier-Stokes all over the domain, where U is the volume average velocity. But of course, you have to take into account that there is a capillary force which acts on the diffuse interface, not on in the pure phase. Of course, you don't have it, but you have it in the epsilon with region. And then you have also to take into account that normally the density and the viscosity of the mixture are not constant, but they depend on phi. Okay. That's another difficulty from the technical point. So basically we are using this kind of approach, like the one I just mentioned this. So here you have a diffuse interface, and this width is epsilon. And this is the phase function. It's more convenient, of course. It's more convenient not only because you can prove much more theoretical results. That's it. If you want, this is the justification a mathematician can use. But it's also more efficient from the numerical. Okay. Because you don't, from the topological point of view, you don't need to follow the free band. Okay, it's incorporated in the formulation. Okay. Actually is the level set to phi equals to 0. Okay, so a first formulation of this kind of model is the so-called model H, which goes back to Weinberg and Halpen in 77. And this is a very simple model. I mean, very simple. But in this case, the density is assumed to be constant. Okay, so it's a requirement which may be unpleasant for certain mixtures. Okay, so if you take matched densities, so the two densities are equal, you take the viscosity depending on phi, then you have this kind of system. You see the advective term here, and here you have the form of the so-called capillary force, which is also called Korteweg force. Okay, and you see from this kind of force, which can be written up to redefining the pressure in different ways, but I prefer that way in order to introduce the non-local model. And this one acts only when mu is not constant. Okay, or if you prefer, when phi is not constant. So it acts only when you have a mixing. Okay, not on pure phases. Okay. And this system, subject to different kinds of boundary conditions, has been studied by many people. Here, I just mentioned the main results. The results I consider the main ones by Boyer, by others, and then more recently by Georges Méonville and Tenan. So also the French school contributed to this subject. Let me stress this. Okay. But how to take care of have to eliminate the drawback of having a density which is constant. And this is a proposal. Okay? We are talking about incompressible models. Okay? Then there is also another word of compressible models, but in that case, of course, the mathematical results are very few. Okay? This is a model proposed by Adels, Gark, and Grün. It's also called AGG, and there is a huge literature on that. And this is a model in which is compatible with the second law of thermodynamics. So it's a thermodynamical compatible model in which you have your density, but you also have this additional mass flux called J, okay, which is given by this. So it's due to the mass transportation. Okay. And this is the density. This was proposed in 2012. You can imagine that from the technical point of view, this model is rather complicated because the bad guy in Navier-Stokes system is it. And the modification is just there. Okay. And the regularity of this, since it's mobility times the gradient of mu, you can imagine it's not so high. And this is exactly what happens. In the sense it's not just a coupling, which is, after all, I mean, like studying separately Navier-Stokes and Canadian. This is a strong coupling. So it's not easy to decouple the system. Okay. In the sense that this term here is very bad. And now I will convince you why it's bad. Why it creates complications which are even more troublesome than the ones you meet when you are dealing with the Navier-Stokes system. Here you have mass conservation in the sense that it's easy to show that the density, there is a transport equation of the kind satisfied by the density given U and J. So the density flux is transported by the velocity and diffused by the components, by the mixture. And moreover, if you take usual boundary conditions, I mean, like for instance, no slip for U, no flux for phi and mu, and or periodic boundary conditions, then you have the conservation. This is an important feature in phase separation. Okay. There are results about these models. There is a literature. Okay. There is a literature, in particular, also with I mean, non-standard boundary conditions, which are physically more relevant, say, for a reason which I have no time to explain. The fact that the diffuse interface is not necessarily perpendicular to the boundary, okay, but it can move like this. Okay? And so you need to introduce a more complicated dynamic boundary condition in order to take into account this movement, but this is very good. So you have a list of results, but all these results are related to the classical Canadian equation, not to the normal Canadian equation. There's a difference. And you also have, more recently, you have these results with constant mobility, in the constant mobility case. Okay, so you see the dates are very recent, the years are very recent. There is also a recent result in the multi-component case, in which instead of having two species, you have n species in the Canadian equation. So that's even more complicated, but constantly. So there are results, the results you might expect. In 2D, you can say many things. In 3D, of course, you can say either, I mean, the existence of a global weak solution or the existence of a local solution for small times. The typical things you can prove for the Navier-Stokes system. Can go beyond. Okay, and then you can also prove, I mean, other results like these are particularly meaningful in the sense that in 3D, for instance, you can prove exploiting the fact that Navier-Stokes system, the weak solution becomes strong for large times, then you can prove, taking advantage of the regularization of the Cannier equation, you can prove that any weak solution does converge to a single equilibrium, even in 3D. Okay, so this is a non-trivial thing, because you have to play with the equations. You have to gain the regularity from the Cannier equation, and then you have to reflect the regularity in the Cortele force in order to apply the Leray result for those terms. Okay, the non-local version. In the non-local case, you see, mu is like this. What is the main difference? The main difference is that now the Cannier equation is a second order equation. It's no longer a fourth order equation. So the regularity you expect for phi is less than the one you have in the classical case of a fourth order equation. Okay? So this is complication. This is not easy. The fact that your phi takes values in between -1 and 1 is related to the fact that here you have the Boltzmann-Gibbs center. It doesn't come from any maximum principle. There is no maximum principle here and also in the fourth order case, simply because the maximum principle does not work. So it comes from the entropy. Okay. And here you have two basic results in the non-degenerate case, so when the mobility is strictly positive, and also in the case where the mobility degenerates at pure phases. So it's 0 at 1 and -1. Okay. And an interesting thing you will discover why just at the end is that in the degenerate case, you see, you can say a little bit more. This cannot be true in the classical Cannier case, because the degenerate mobility is much more difficult than the constant mobility case. But in the non-local case, it's the reverse. I will explain you why, but in the end. Okay. Then there are also more recent results about the so-called convergence non-local to local. So when you keep this term here, so when you approximate the gradient square with the non-local operator, and you take a family of kernels which converges in an appropriate way to the delta, to the Dirac mass, essentially, then you can recover a solution. You can link essentially the non-local mode to the local mode, okay, in a rigorous way. Okay. So these are results in this case. They are in blue because you need this. So. Okay. So the results I'm going to talk a little bit about regard the case in which you have constant mobility, but you are in 2D, in 2 dimensions. So one may wonder, because the former results were already existence of a global solution in 3 dimensions. But our question was, what can we say in 2 dimensions? Normally in 2 dimensions, you can say many things. And here I will show you that you can say, not many, but some things, okay? Additional things. And the basic things are this. You can prove the existence of a global solution, some solution. You can prove that any global strong solution, this is very important. Have you seen the double well potential, okay? The minima of the double well potential are not the pure phases, are mixed phases. So what you expect? You expect it's a gradient flow. Think of Cannier equation 1. You expect that your phi stays uniformly away from pure phases in finite time, because it goes closer to the minimum. Okay? But proving this is very, very, very difficult. And it has been proved even in 3D only recently, using the Georgian iteration method. So it's not true. So we prove that this is 2D, so it's a little bit easy that they stay away from pure phases in finite time, any global storm solution. Global storm solutions which are separated at t equals 0, so the initial datum is already separated, are unique. And so you can say that any weak solution can have a unique continuation as a strong solution, and it converges to a single equilibrium. In the matched densities case, you no longer need the fact that the initial data must be initially separated. You can still prove the uniqueness of such. Note one thing, I'm talking about uniqueness of strong solutions, not of weak solutions. That's open. In Navier-Stokes 2D, you can prove uniqueness of weak solutions, but not not for the moment. And then, moreover, we can prove an estimate which shows how close a solution or to a matched density model is to a solution to the unmatched model, in which the density is changes. So these are the results. Now I will be brief on these technical things, but you have a domain which can be Lipschitz in the 3 dimensions, simply because you need to prove the existence of a global weak solution. You need more regularity in 2D because you want to prove the existence of a strong solution. You have a viscosity satisfying your usual assumptions. And the interaction kernel is W11, so it's a smooth kernel, not a singular one. And you take a U naught and phi naught, the 2 initial data in the reasonable space. Of course, the entropy must be in L1, and you take the mass average of the initial datum less than 1. Why? Because you want phase separation. You cannot start from a pure phase. If you start from a pure phase, you don't have any separation. You start from a pure phase, and that's it. Okay. And then this is the result by Frigeri about the existence of a global weak solution. I mean, it's not a problem to have a look at the details, but look only at one thing. This is in L43, 4 over 3, and this is okay. Everybody knows this. But it's here in the dual space of H2. So the solution to the Navier-Stokes system is weaker than the classical LL solution. And it's weaker because of this, which does not allow you to formulate the equation in the dual space of H1 divergence. So this is the background. So this is the result by Frigeri, who is, by the way, for the student of mine, just to be, we are connected. And then you have the energy inequality. This is true, okay, when the energy is this, in this case. So entropy, the mixing term, and the classical kinetic energy of the Navier-Stokes. This is the result about the existence of a global storm solution. Okay, you have a list, of course, of properties, you can imagine that. But once you are able to do this step, everything gets simpler. The point is to get the step, and this is not easy. And the point is the action. Okay? And basically you have this, okay? You can write down the equation almost everywhere, or the system almost everywhere. The conditions are I forgot to mention, the conditions are, in this case, no slip for the velocity, and the normal flux of the chemical potential is 0. You don't have any boundary condition on phi, because this is an equation of second order. It's not a fourth order equation. Okay. Then, main ideas to prove this kind of results. The main ideas are this. We have used a semi-Galerkin method, in the sense that we have taken phi in a suitable finite dimensional space. We have solved the Navier-Stokes system, and then we have constructed a map, a finite dimensional map, through the finite dimensional solution to the Canadian equation. Okay. But in order to do that, you need first the existence of a strong solution to the Cavalier equation when the convective term is just a LRA solution. So L4 into I mean the serving condition. Okay. And then you also need the boundedness of phi. That's the reason why, because one may think, okay, but approximate the entropy, okay? This is done in many cases. But if you approximate the entropy, you lose the property of boundedness of phi. And this is bad. Okay? That's the reason why. And moreover, we also need a suitable interpolation estimate for the pressure, which was not known, I mean, as far as we know. Okay? And why you need this suitable interpolation estimate for the pressure? Because in order to produce a higher order estimate, you multiply by the Stokes operator of U, but you have a viscosity which depends on phi. And from there, the pressure pops up, and you have to estimate. Okay, that's the reason you need a special estimate for the pressure. Then we can prove the separation and uniqueness of strong solutions. Okay, so by separation, I meant this. I mean this. For any tau positive, you can find the delta depending on your tau. Okay, such that the supremum of phi is the infinite norm is less than or equal or minus delta. So your phi stays in between -1 plus delta and 1 minus delta. And this is a big advantage because your entropy, which is singular at the endpoints, because you have the derivative, becomes Lipschitz. Okay, but you have to gain this. Okay? And thanks to this, you can prove uniqueness, okay, and also continuous dependence of the initial data, exploiting the separation, okay? Exploiting this condition. And then you can say that if you have a weak solution, then you can extend your weak solution uniquely as a strong solution starting from some time, okay, using the previous results. And you can also write down the energy identity, but not starting from the initial time, only starting from tau on. So you see, you have some results, but you don't have the results you had in the two-dimensional case for Navier-Stokes or for the H model, the model in which the densities are the same. Okay? So this is more difficult. Okay. And then you can prove also this result. Any weak solution converges to 0 and phi infinity, where phi infinity is the solution to this system here, okay, which is the stationary non-local problem. This is a typical result in this Caniglia stuff, and it is obtained by using a special tool which is called Lojasevic-Simon inequality, which holds for real analytic nonlinearities. It's a very special tool, because in general, if the nonlinearity is not as smooth as a real analytic, you cannot prove this. There are counterexamples, even easy counterexamples. Comments on the proof. Comments on the proof, I would like to stress one thing. Okay, this I already told you about this. You see, here, the point is that you have a complete well-posedness only if the initial datum is separated from the beginning, I mean, initially. And so you have solutions which are not only strong, but also separated from pure phases. In that case, you have well-posedness in the sense you have a unique global strong solution. Okay. But otherwise, it's not true. I mean, we are not able to say that. Okay. So it's very restrictive with respect to what you know in the simpler case. In the matched, I mean, you may wonder, okay, but can we compare the solution to the model, the AGG model, so the matched case with the solution to the matched case, and to say when they are, if the densities, the two densities are close, are they close? And you can do that in the sense that you have, for instance, a strong solution with initial datum which satisfies the strong assumption. Then you have this kind of estimate. This is for uniqueness. Okay, I'm talking. Sorry, I anticipated what I'm going to say in a minute. Okay, this is the estimate you can get, which gives you the uniqueness. I mean, the one I mentioned before. So you have initial datum separate such that this is separated from the first. And then you can produce this kind of estimate. Okay. But you see, you need strong solutions. You cannot do it for mixed. I mean, we cannot do it for mixed. And the point is that this QT, you see, this QT, which is here, this QT depends on these norms here. And this RT depends on this. And even here, the interpolation inequality is essential because in order to, you write down the equation for the differences, and then what you do on the Navier-Stokes equation, you cannot multiply by U1 minus U2. You have to multiply by the inverse of the Stokes operator, U1 minus U2. But again, the pressure pops up and you have to handle it. Okay. So also in this case, the interpolation for the pressure plays a role. Then finally, we have the stability. So you have a strong solution to our model. You have a strong solution with constant density. Okay? They are both originating from the same initial datum. Okay? And you can estimate the difference in this norm, the difference of the two solutions in terms of the differences of the densities. Okay? With respect to the reference density, which is this. Okay? Written in this way, it's not completely clear, but if we write down in this way, this is more clear. So ρ1 is the reference density, ρ2 is the reference density plus epsilon, and then you get this estimate. So if the densities are sufficiently close, then the solution to your matched density model is close to the solution to the unmatched density. Okay? This is provided you have, of course, strong solutions. And also here, you still use the inequality for the pressure. So let me finish with some remarks about what to do or what can be done in three instances. So one may wonder, okay, but can you prove, for instance, the local existence for small times of strong solution, or other things which are true when you consider the local Canadian equation, the former one, okay? And this seems a bit hard because this is very different. This is the term, the additional term, okay? This does, I mean, it's unclear because we don't have a regularity enough. But perhaps we have more chances when you have the mobility, the degenerate mobility case. Why? Because if you have the degenerate mobility case, then the principal part of the equation can be written in this way. You can split the chemical potential, and you can take advantage of the fact that the entropy, the second derivative of the entropy times the mobility is nice. In particular, it's constant if you take 1 minus v squared for this and the Boltzmann entropy for this. Okay? And so you have a Laplacian here, and then you have the demixing term here. And so you hope, I mean, this is a hope, because even if you have a LRA solution, then maybe you can prove the existence of a strong solution to the Canadian equation, and then the machine starts. Okay. So this is a hope. You cannot do that when you have constant mobility. It's more complicated, okay? Because you have the entropy, and that's it. You have divergence of S prime gradient phi. Okay. One may wonder, okay, but the model H, at least you can say something more in the model H. So in the case in which the densities are equal, okay, there is a number of results about which goes beyond the mere existence of a weak solution. They are listed here. In 3E, something can be done in the sense that there is a recent result by Urban, Knopf, and Boyarty about the convergence from local to local for more times of a local strong solution, but constant viscosity. Okay. And we are writing down the existence and uniqueness of a local strong solution with non-constant viscosity in the non-local case. This is the state of the art for the moment. So let me conclude remembering two masters who are, I think, very well known to some of you, and also to me, of course. Jacques-Louis and Enrico Mangenes. Enrico Mangenes was the head of my lab when I was at the beginning of my career. So, I mean, they are a very special person to me. So thank you very much for your attention.
At some point, you said you were using the Simon inequality, but what is analytic?
The entropy.
What function is
The entropy. The Boltzmann-Gibbs entropy is analytic. It's real analytic in when you are away from -1. That is the reason why you need to prove the separation, because otherwise you cannot prove, you cannot use the Rosetta in the local.
Actually, I have one. So you mentioned that there were a bunch of reasons that called for two linear discodes that you don't have here. I was wondering about the weak strong uniqueness. So if you start from an initial data that is separated, but you build a weak solution, that coincide with the strong one? That's
a good question. In the matched density case, you can do it, but in the unmatched density case, in that case, we don't know. We don't know. Yes. Okay. It's an interesting issue, of course. Also because for the continuation of the solution, yes.
Question. There is still a problem with the mustard. I understand the vinegar on the oil, but where is the mustard?
This is a very interesting question. This is a very interesting question because mustard is a surfactant. And we are studying, indeed, now with a colleague of mine at Fudan University, we are studying models of this kind in which you take into account also the effects of a surfactant. Okay, so models in which you have exactly the phenomenon, the right vinaigrette. I mean, in a sense, you have a species which breaks down the bonds between the molecules of oil.
But then you have to.
Yes, yes, exactly.
So speaking of the phase, that's enough. You need a system.
Exactly. Yes. So you have a system for the velocity of the fluid, a system for the order parameter, and the system for the density of the surfactant. And the most important thing is are the interaction terms in the free energy. Yes.
Your function J, you mentioned was W11.
Yes.
So, I mean, it's not really smooth, right? You still have the examples log of log that can blow up.
I agree. No, but I use the word smooth for a specific reason, in the sense that when you are talking about fractional Laplacian and stuff like that, then your current must be similar.
Yeah.
Only for my comparison, it's not smooth.
But but then what is the fine property? Because it's not bounded necessarily. So what can be optimized there?
No, the point is that when this is a very important question. I just give you one of the important things. There are many, but the most important is this. You want to prove the existence of the phi in H1 because otherwise, because you need a diffuse interface. You cannot have jumps. If you don't assume that you have a gradient of the interaction pattern, you cannot produce an H1 estimate. So it's important in order to gain some spatial regularity from the phase.
It's more of being able to write terms rather than
Yes.
just bounding.
Yes.
Okay, thank you.
I think there was a question online. There was a
Yeah.
hand raised, but the hand disappeared. So if you are online and you have a question, then you can just maybe unmute yourself and ask the question. Okay. Okay, well, if there is no online question, let's make Maurizio again.
There is still something strange in this
Yes.
ADG model.
Yes.
Why isn't it symmetric in row one, row two? There is an asymmetric term, so that's puzzles me.
What you,
When you create the model at the very beginning, I mean at the beginning of your ADG part, before, so the G has an asymmetry. In row and row two, and I would expect it's, I mean, this kind of thing that I agree, but
but
why?
the flux can go from one species to another.
But
Or back.
But why one and two?
I mean,
It should be symmetric. It's,
It should be symmetric, but you have to choose in the sense that the flux certainly is zero when the density is
so row one is higher than row
Yes.
two, for example, something like that.
Exactly.
Okay.
I have two questions.
Yes.
The first one is your kernel J
Mhm.
is assumed to be symmetric.
Yes, exactly.
But omega,
This is an interesting.